by structural engineering principles at reaction calculations. Newton's third law, there it is there. We're trying to get equilibrium, so we're trying to say everything downwards is equal to everything upwards, because otherwise it would keep going upwards or it would keep going downwards. That's kind of the concept. So we're trying to work out A and B. We're trying to work out what the minimum requirement is for the columns, so that they don't get crushed by the downward forces. Or yeah, that's it really. So we can't work them out because we haven't got B or A in isolation. So what we do is we use what we call bending forces, bending moments. Here's some pictures to help you. So if I put a pin in A, I've either got stuff to the right or stuff to the left. It's either pushing down or it's pushing up to the left or the right. And what that's doing is it's causing a bending moment, a momentum in a direction. Now the direction is either causing the material to go in a clockwise direction or it's causing the material to bend in an anti-clockwise direction. So if you think about Newton's law, anything that makes the beam go in a clockwise direction from A should be equal to anything causing it to go in an anti-clockwise direction, and that would cause equilibrium. That would mean it's stable, it's not bending in either direction because it's cancelled out. Okay, it's the same. So what we do is we say, well, actually that's fine then. So everything causing it to go in a clockwise direction, so the 50, the 30 and the 40, if you look at the A and you look to the right of A, 50, 40 and 30 are pushing downwards. It's causing it to go in it's bending in a clockwise direction. So that's all on that side. And then anti-clockwise is anything to the right that's pushing up or anything to the left that's pushing down. Nothing to the left is pushing down, which is fine. So the A and the B are both pushing up, so I put the A in there as well. But you've got to remember the idea of momentum moment is the further away you get from the point, right? So the point of A, if you are at A, there's nothing causing, if you've got a force on top of A or underneath A pushing up or down, it's not causing it to bend. So it's cancelled out. And the way to do it in the formula is just times it by 0 because there's 0 distance from A. So if you do A times 0, it is 0. So A is therefore cancelled out. The B is 5 meters away, it's pushing upwards, it's causing it to go in an anti-clockwise direction, so that would always be there. So if you follow this through, what you end up with is this concept of this momentum, the moment, kilonewton times meters, and our kilonewton meters, 5B, is equal to 380. To get the kilonewtons by themselves, the B value, whatever B represents, you would then divide it by the distance from A. Don't forget, because we're doing all of this from A, yeah? So this calculation will only work if all of these values you multiply by the distance from that one point, which is A. That will isolate and give you B. That makes it really easy then, because once you've got B, if you go back to our original step, A plus B equals 120. Now we know what B is. We can substitute that in to find A, which is perfect. So a way to check is to say, well, we've got our new values A and B, so they need to equal 120. So remember, equilibrium, downward equals upwards. And if they do, then that's great, it's equal, and that is correct then. My calculations are all great. So I know what A and B are, I know what those reactions need to be. So those columns, so column A needs to withstand 44 kilonewtons at least, and column B needs to withstand 76, otherwise it will buckle, it will break. Okay, just a quick note, if you were wanting to do it slightly different or to double check, triple check maybe, you can do it from the other way. So you can say, do you know what, from B, I'm going to put a pin in B this time, and I'm going to calculate all of the moments from B. So that is the force times the distance, either causing the beam to bend clockwise or anti-clockwise from B. Pin in B. What's that going to do? If you held B and you push down to the right, it's going to cause it to go in a clockwise direction. And if you push up from the left, it's going to cause it to go in a clockwise direction. If you push down from the left, it's going to cause it to go anti-clockwise, and if you push up from the right, it's going to cause it to go anti-clockwise. So if you use that principle, you will see that's what I've applied here. Everything causing it to go clockwise from B and everything causing it to go anti-clockwise from B. I've followed through step 2, and then you then re-substitute in, and you'll see, just using exactly the same concept, I've got the same values, and that means my calculations are correct. I hope that helps, and yeah, wish you the best of luck with this. Thanks. Bye.